Welcome back, students. In this video, we are going to look at intermolecular forces. So let's just review really quickly what an intermolecular force is. An intermolecular force, which we often abbreviate as IMF, are attractive forces that exist between molecules. Now, the key here is it's between molecules, because a lot of times there's a misconception that's developed where students think that it's within a molecule, but it's really between two separate molecules. These attractions end up occurring because of the dipoles of different molecules. So here's a really simple diagram where on this side I see a partial positive for one side of a molecule and a partial negative on that same molecule. Well, a neighboring molecule is going to have a partial negative and a partial positive. And the key is that the positives and the negatives are going to be attracted to each other, right? So this is an attraction. So they can be attracted to each other like this diagram on the left is showing. They can also be attracted to each other kind of like end to end. They can also be attracted end to end. So here's an attraction that's showing the end to end. So also an attraction where one side is partially negative and the other side is partially positive. So these attractions are there because one end is positive and the other end of another molecule is negative, and like magnets, they're attracted to each other. Remember that these are intermolecular forces, which means between molecules, whereas intramolecular forces are chemical bonds. So intramolecular forces would be like covalent or ionic bonds. Intramolecular forces are really, really strong. These intermolecular forces between two molecules are much, much weaker than chemical bonds, but they still have an effect on chemical properties. So let's talk about the different types of intermolecular forces. I'm just going to give you a quick overview here, and then we're going to look at each one individually. So when you have something that contains an OH, NH, or FH bond, then you have an extremely polar bond within the molecule. That super polar bond ends up creating a situation where you have a big dipole. And so because all of these examples have a hydrogen in them, we call the intermolecular force that exists when you have an OH, NH, or FH bond hydrogen bonding. Biggest misconception here, it's not actually a bond. It's not a covalent bond. It's not an ionic bond. It's not within a molecule. It's between two molecules. And it happens because hydrogen is so weakly electronegative, whereas oxygen, nitrogen, and fluorine are your three most electronegative elements on the periodic table. An example of this would be something like methanol. So methanol, which is one carbon and an OH attached where that carbon has the remaining bonds or two hydrogens, this is going to be something that is capable of hydrogen bonding. Notice the wording that I used there. I didn't say this hydrogen bonds. I said it's capable of hydrogen bonding because in order for this to hydrogen bond, it needs another methanol molecule to hydrogen bond to. So hydrogen bonding is the strongest of the intermolecular forces. I'm ranking those intermolecular forces in comparison to covalent bonds, whereas dipole-dipole forces are the second strongest. Dipole-dipole forces exist within molecules, between molecules, where the molecule has a polar bond but lacks an OH, NH, or FH. So something like an ether is going to be polar but not contain an OH, NH, or FH bond, and thus is capable of dipole-dipole interactions. London dispersion forces exist when you have nonpolar parts of a molecule. Notice how we said that the strength of this is variable. It depends upon how big the molecule is. So for small molecules, this is going to be really weak. For really, really big molecules like wax, which is C25H52, it's going to be strong enough so that wax is a solid at room temperature. Here, London dispersion forces are going to exist between molecules that are only nonpolar. So something like ethane. Now let's look at each intermolecular force individually. So we're going to start with hydrogen bonding. In the wording here, I said it's a specific, strong dipole-dipole interaction. So hydrogen bonding is just like a dipole-dipole interaction on steroids, right? It's like the Hulk of dipole-dipole interactions. This is just a really, really strong dipole-dipole force. So strong that it gets its own name. The hydrogen is going to bear a partial positive charge, and I'm going to use the simplest molecule possible, which is water. So your hydrogen has a partial positive, your oxygen has a partial negative. So another water molecule is going to be attracted to this water because another water molecule is going to have a partial negative on the oxygen and a partial positive on the hydrogen. And that attraction is going to be these dashed lines that I'm highlighting in yellow, right? The attraction between the two molecules, that is your hydrogen bond, right? So this right here is the hydrogen bond. If we could go back in time, I would change this word. I would not call this a hydrogen bond. I would call it a hydrogen attraction or a super dipole-dipole attraction, literally anything other than the word bond, because bond leads to so many misconceptions. So the cool thing about things that can hydrogen bond, like water, is they're hydrogen bonding all over the place. Like this diagram on the right is showing, we're seeing loads of attractions here. We're seeing that the positive on this end is attracted to the negative on the other end, right? And more attractions and more attractions and more attractions and more. And yes, there are some repulsions as well, but the attractions end up winning out. When we're looking at hydrogen bonding, these attractions are so strong of an intermolecular force that they actually play out in the molecule's boiling point by raising boiling points. And we're going to talk about that in another presentation. Now let's look at dipole-dipole interactions. Dipole-dipole interactions, I actually have the same diagram here. So we're going to just imagine that in our dipole-dipole interactions, what's happening is we have a partial positive on one molecule and a partial negative on the other molecule. They're attracted to one another, but the partial positive and negative just aren't as big as they are in hydrogen bonding. When something's capable of hydrogen bonding, it's because the dipole is massive. Whereas in dipole-dipole interactions, you still have the same kind of heart of what's going on. You have a partial positive and a partial negative, and they're attracted to one another. It's just that these aren't as strong of a dipole. So something that can do dipole-dipole interactions is acetone. So acetone looks like this, and I'm about to abbreviate the hydrogens that are attached to these carbons. So instead of drawing a bond to each of them, I'm just condensing them because I'm tired of drawing Lewis structures. We have a carbon-oxygen bond that's polar. We have carbon-carbon bonds that are nonpolar and carbon-hydrogen bonds that are nonpolar. So here we have a polar part to the molecule. So what would end up happening is another acetone molecule would just be attracted to this one and they would just line up. Right, this one is polar this direction. And their attraction would be in this area because here this carbon has a partial positive and this oxygen has a partial negative. And so dipole-dipole interactions really look a lot like hydrogen bonding interactions. The difference is the strength of the dipole. Now let's look at London dispersion forces. London dispersion forces, I think, are harder to imagine. So first, let me draw your attention to the left-hand side here, where I'm trying to illustrate that we have just something with a nucleus, right? So pretend that this is maybe, like CH4. So you've got a nucleus and then you have a cloud of electrons around it. And what happens is your cloud of electrons is kind of like water in a bathtub. It can splish and splash and swirl and be more on this side and less on this side. Like, have you ever seen a 5-year-old take a bath? Imagine a kid taking a bath that they're playing in and how the water is never going to be level. They're always splashing. And that's what your electron clouds are like. Your electron clouds can be maneuvered. At any one moment, because electrons are moving all the time, the electrons can swish to one side. And when they swish to one side, what happens is that side that they swish to has a partial negative now. And that the side that we've swished away from now has a lack of electrons, which is the partial positive. And so once the molecule has this situation where the electron cloud has moved to one side or the other, a temporary dipole has been created, right? It's not permanent, it's temporary. So a temporary dipole has been created, and that temporary dipole induces another temporary dipole on the neighboring molecule. So once you have a partial positive here, then a partial negative forms on the neighboring molecule, which then inside that molecule, then you have a partial positive on the opposite side because now you have a lack of electrons, which induces on the next molecule a partial negative and then also a partial positive, and this just keeps happening. And the more carbons that you have in your structure, the more opportunities there are for partial positives and negatives to be created. And it's almost like every time there's a little partial positive negative in a molecule, it's like it's a small magnet. And so if you have a really long molecule, you have lots of tiny magnets that are going to attract to another molecule. And that's why for London dispersion forces, size matters. The bigger the molecule, the stronger the force. So let's go ahead and write that down. Right, so that the bigger the molecule, the stronger the force. This matters because it plays out in how molecules have certain physical properties, which we'll talk about soon. So I want to make an intermolecular force flow chart with you, because if we are looking at a molecule, I want you to be able to look at that molecule and decide what is the strongest intermolecular force that's present for that molecule. And I notice that I say strongest intermolecular force because really, when you're looking at something that has a nonpolar section and then it has an OH at the other end, it's going to have all of the forces. But it's really difficult to rank the strength of intermolecular forces if you're looking at every single force. So a lot of times what we do is we just focus in on the strongest intermolecular force that is present for a particular molecule. So what I want to do is start our flow chart with asking ourselves a question. Is the molecule polar? So that's going to be the question that we start with. So yes will go one way, no will go the other way. So yes and no. All right, if your molecule is nonpolar, there's only one force you can have. And that one force that you can have is your London dispersion forces. Some people might call London dispersion forces van der Waals forces. I like to call it London dispersion forces because then I can abbreviate it LDF. So if my molecule is nonpolar, then all I can have is London dispersion forces. But what if the molecule is polar? So if your molecule is polar, you need to ask yourself another question. Is there an NH, FH, or OH bond? So yes, we go one direction. No, we go the other direction. If your molecule is polar and has an OH, NH, or FH bond in it, then what you will experience, the greatest intermolecular force that you can experience for that molecule, is hydrogen bonding. Whereas if your molecule is polar, but there is no OH, NH, or FH bond, then the strongest intermolecular force that that molecule can experience is dipole-dipole. So hopefully you can begin to use the flowchart to help determine which molecules experience what forces. In this video, we talked about the 3 types of intermolecular forces and looked at examples for each of them. You want to know their relative strengths, because when we move on to our next section and we look at how these intermolecular forces affect physical properties, you need to know which intermolecular forces are stronger than the others. Then, if you're given a molecule, you definitely want to be able to determine what the strongest intermolecular force is that that molecule can experience. Keeping in mind that if something can experience hydrogen bonding and there's also a section that's nonpolar in the molecule, it also has London dispersion forces. And it probably also has dipole-dipole forces. In this video, we just looked at how to determine what the strongest intermolecular force is that a molecule experiences. Thanks so much for your attention. This is Katoni signing out.